Thank you, Augusto, for the introduction. I'm presenting on behalf of Chengyue Wang. Unfortunately, she couldn't join us today, but she will be there on Zoom session after to take any questions. So let's dive in. Today, I'll present reconfigurable stream network architecture. Nowadays, we know AI hardware spans a diverse spectrum. So on one end, we see general purpose CPUs, that can run all kinds of workloads. And on the other hand, we have ASIC, which is more specialized. And in between, we have GPUs, CGRAs, and also FPGAs. So we see progressively more specialized data paths that trade usefulness for efficiency. With so many hardware options available, a natural thought is, instead of picking only one, why not we co-locate different hardware to leverage the best of each? And that's what exactly the AMD Versal device does. So AMD Versal AI Core Series reflects this trend where we combine CPUs, FPGAs, and AI engines on a single SoC. AI engines are dedicated computational resources to deliver high performance and energy efficiency for AI application, while FPGAs can offer high flexibility in data path customization. So we know this idea sounds really great that we can have multiple resources. However, to get the best of both worlds, we cannot do that really easily. It's really challenging. For example, spatially, every hardware speaks its own dialect. It is tricky to coordinate diverse hardware components with distinct execution model and resource characteristics. And temporally, we see here DNN layers have different operator shapes across layers. And within same layers as well, there are different phases like prologue, steady state, and epilogue. So this diversity makes it really hard to orchestrate heterogeneous resources for high utilization. Therefore, this work wants to create an instruction set architecture that can sit on top of these heterogeneous devices. And this interface can abstract away hardware details for software and to have a unified software and have an efficient control. And we know that there are two conventional types of ISAs. So there's a fine-grained ISA where we use one instruction to control individual scalars or short vectors. However, this is unnecessarily control-heavy, especially for DNN execution, and has large overheads. Intuitively, we don't really need to describe the data movement of every data one by one inside a DNN layer. On the other hand, we have a coarse-grained ISA, which uses one instruction to control the entire DNN layer, or you can also think about it as a sublayer. This approach is very low in control overhead, but it is very inflexible. The execution of layer is serialized, and only one layer can run at a time. So therefore, the question this paper aims to solve is that, can we design an ISA that is control-light but still sufficiently flexible? So therefore, we are trying to have this goal where we rethink the hardware and the software interface for DNN domain. And we make 4 key observations for DNN Accelerator. First, data movement dominates throughout the execution. Second, the optimized software needs predictable hardware. Third, the DNNs have low information entropy in control. Lastly, the specialization drives growing hardware heterogeneity. And based on these insights, we propose RSN, which is Reconfigurable Stream Network Architecture. RSN abstracts the data paths as a network of functional units, as shown in this figure. Let's go a bit deeper into how this works. The node and network are stateful functional units. Functional units abstract virtualizes compute and memory resources, turning them into a software controllable objects. Because the functional units are stateful, they can preserve the data across instruction, which help abstract memory resources. And each functional unit is specialized and composed of a different combination of building blocks, which includes decoder to understand instructions from software. We have input-output data ports to communicate with other functional unit. We have transformation logic to perform operations. And then we have state holders like buffers or registers to preserve data. Each edge in the functional unit network is a stream FIFO that connects each producer function to another consumer function unit. The data path is latency insensitive, meaning that a function unit can stall while waiting for the data. And this is also very hardware friendly. There's no need for global arbitration to track data dependencies. And the network is completely circuit switched, which means that there is a dedicated exclusive path between two nodes, which will be built when they talk with each other. So the circuit switch network and also a stream connected interconnect unifies the representation of communication. And the stateful functional unit unifies the representation of compute and memory resources. In RSN computer, program is a computation, meaning triggering a path in the functional unit network. Software views a computation phase as a decomposable pipelined path. So therefore, unlike von Neumann computer on the right, where the program state live in the memory or register, the program state in RSN computer on the left is distributed across the functional unit network. And the software is programmed with high-level information on stream. So one instruction controls one action on one functional unit. It tells information such as where the data stream to and fro, what transformations to perform, which data to preserve, and the length of each stream. So these kind of instructions are, information are part of the instruction control. And as shown in the picture here, the instructions are issued to the data path through an instruction decoder. Once both the producer of the data are ready, the path is triggered and the data begins to flow. Let's look at some of the advantages of this RSN architecture. The first key advantage of RSN abstraction is software can be flexible control of data movement. So RSN can dynamically orchestrate resources via decomposable computation paths and predictable hardware behavior. A computation is mapped to a path of multiple decomposable pipeline segments. Along the path, every function unit acts in a deterministic manner, which is pretty important. And therefore, the execution of computation is predictable to the software. For example, if we consider an RSN computer just specialized for GEM, each GEM uses a path of many segments to load the input from off-chip for compute and also to store output back. This animation here shows an RSN computer with two compute functional units and can support two different kind of mapping patterns, for example. When we find one gem layer is compute bound, two independent paths can be triggered to exploit spatial parallelism between two output tiles. While when we find layers are memory bound, we can choose to fuse two layers together in a pipeline manner. And the output of the first layer can directly feed into the input of the second layer. And the intermediate feature map between two layers does not need to be moved off-chip. With the same principles of simple example we just explained, we prototype RSN XNN as an RSN computer for transformers on AMD Versal VCK'190, where we have both AI engine and FPGA on the same SoC. The design virtualizes the FPGA fabric and AI engines into 22 coarse-grained functional units, and we evaluate everything on a real board. So this slide takes a closer look at the instruction specialization for RSN XNN. In total, we define 8 instruction types to cover 22 functional units, and each instruction is highly specialized for their target functional unit in terms of its own bit field, layout, and length. For example, we have memory A instruction at the top that has bit field for the shape of mattress to read and write, and flags to indicate whether to read into the current functional unit or write out of the current functional unit. While we have another instruction, memb at the bottom, that has a size field to control the length of the streaming data to route, and a bunch of flags to indicate where to read and write the data. So that's one of the advantages we have of RSN. And in addition to the flexible control of the data path and the data movement, the second key advantage is low instruction level intervention. So RSN leverages DNN's low control entropy via flexible instruction to data granularity, and can concisely handle hardware heterogeneity via coarse-grained heterogeneous functional unit abstraction. Let's try to understand a bit more of that. By specifying different length of the streams, one RSN instruction can span an entire layer for low-cost control or zoom into multiple data for flexible control. Because, as we mentioned before, DNNs are very control light compared to the data process. Most of the instruction will stay coarse-grained. And in our RSN XNN prototype, 1 byte of instruction can drive up to 1.6 gigaflops of FP32 compute. And on average, 100 instructions are used per millisecond. Therefore, the overall instruction level intervention stays very low. And we know as nodes in a network differ quite from one another, the RSN abstraction can efficiently virtualize heterogeneous hardware resources by separating the control from the data pipeline and enabling low instruction level intervention. So as shown in the figure here for RSN XNN, functional units are very coarse-grained. For example, we have, in this example, 6 functional units implemented on AI engines, and each can deliver 1 teraflop of compute in FP32. And we also have some functional units that are very different to one another. For example, memory functional units on the FPGA side that have very little or even no floating point compute capability. And the idea of network naturally embraces this kind of coarse-grained heterogeneity. Let's look at the performance analysis when compared to FPGA-only implementation. On the same board, ISCA'25, RSN XNN is 6 times better in latency and 2 to 3 times better in throughput. We also benchmarked RSN XNN against NVIDIA's T4 and A100 GPUs using a large transformer workloads that saturates all the 3 platforms, all the 3 respective platforms. And T4 has the same 8 teraflop performance as ISCA'25, and A100 has the same process node, a 7 nanometer process node. And even with much lower off-chip bandwidth, RSN XNN matches the T4 latency while delivering 1.8 times better energy efficiency. And when we compare to A100, it achieves lower latency, but roughly 2 times better energy efficiency. So our approach of having this abstraction really helps to get really good results. We also performed overhead analysis. The average RSN instruction processing rate is 1.4 megabytes per second, which is negligible. And the energy of instruction decoder only occupies about 0.08% of the 0.08% of the total power. And the area cost of instruction decoder is 2 to 3 times of the total FPGA design area. Overall, the overhead of supporting RSN ISA is very low. And there are many more results we provide in the paper, so I would recommend to have a look. And RSN XNN is fully open source for the community usage. So to conclude, RSN introduces a network abstraction at the ISA level for domain-specific accelerators. RSN architecture naturally aligns with AI workloads and heterogeneous hardware. Data movement is the first-class citizen in RSN programming, and we believe that RSN has the potential to be applied beyond DNNs as well for other streaming applications as well. Thank you for your attention, and RSN XNN code is fully open source on GitHub. Thank you.